We have another example problem here. As a steel guitar string vibrates, the component of the magnetic field perpendicular to the area of a pickup coil nearby is given by the equation B as a function of time is equal to 50 milliteslas plus 3.2 milliteslas times the sine of 1046 pi times t. The circular pickup coil has 30 turns, a radius of 2.7 millimeters, and a resistance of 0.1 ohms. What is the magnitude of the maximum current induced in the coil? So on a guitar, this would be something like an electric guitar. We know already that if we pluck the string of a guitar, it vibrates back and forth, oscillates back and forth. That oscillation here, I'm assuming that it's telling us that this string itself has a magnetic field around it. It's telling us that there's a pickup coil nearby. I don't know exactly where it is. I don't know the total makeup of an electric guitar. But just from the wording of the problem, there's some sort of pickup coil that as the guitar string vibrates, there's a magnetic field that passes perpendicular. So this magnetic field that passes into this pickup coil obeys this equation given in the problem. Now, this magnetic field is not the field produced by the coil. This is the magnetic field passing through the coil because of the string. So this is the field that passes through the coil because of the vibrating string. Well, this magnetic field is changing with time. If this magnetic field that is passing through the coil is changing with time, then there is a changing magnetic flux through the coil. The flux that's passing through the coil is also changing with time. So our question wants to know the magnitude of the maximum current induced in the coil. When we see that term, induced, we want to think about Faraday's law. Faraday's law tells us about EMF induced, or voltage induced, which in turn, since they gave us a resistance, we can think of this coil as a little resistor. If it has induced current, we multiply that by resistance, and that would equal the induced voltage. So this is our induced current that we are looking for. So we can write this as I is equal to N over R d phi dt. N is this number of turns, the 30 number of turns. Capital R, since that's my Ohm's law, that's my resistance. They give us a radius of this coil, which is going to come into play for the cross-sectional area. Having a radius implies a circular cross-section. So the area of a circle is pi r squared. Flux, we need the equation for flux in terms of time so that we can take the derivative of it and plug it in here. Okay, so flux. Our fundamental equation for flux is the integral of B dot dA. if I think about this magnetic field, they've already told me that's the component of the the component of the field that is actually passing through this area. This magnetic field totally depends on time, but it does not depend upon any type of distance, a radius. It doesn't depend upon an X, a Y, a Z. That means if I imagine just one exact moment in time, B, this magnetic field, would be uniform in this area. So I can say that the magnetic flux is simply B dotted with A. And since they already told us in the problem that they've given us the component that passes through the area, our flux will be as simple as just B times A. Now, our equation, of course, is changing with time, this flux. So this magnetic flux is equal to this whole equation for B up here, which I'm going to just leave it as B for the moment. Area is just the pi r squared of the coil. The area is not changing in this case. If I come back to my Faraday's law and Ohm's law combined over here on the left and put in this flux, B times pi r squared dt, that's what I'm taking the derivative of. In this case, though, the pi's not changing, the r's not changing. So ultimately, I need to simply take the derivative of the magnetic field in this case. It's the strength of the magnetic field that is changing, and that's ultimately why the flux is changing. And so that's the derivative we need to take. So our induced current, we have the number of turns, we have the radius, which I'm going to put in SI units, we have the resistance. I need to take the derivative of our magnetic field equation up here, but specifically the derivative with respect to time. So this first term, the 50 milliteslas, when I take the derivative, that just goes to 0, because that is a constant. The derivative of the second term, the 3.2 milliteslas, I'm going to go ahead and put that in terms of teslas first. Derivative of sine is cosine, so I'll have cosine of all this stuff. And then I have to take the derivative of what's inside the cosine term. So everything within these brackets represents the derivative of our magnetic field with respect to time. I have the pi r squared, I have the resistance, I have the 0.0032 teslas, that was the amplitude. I have the 1046 pi, and then I have cosine of the 1046 pi t. What this gives me is so all of this stuff in front, I'm rounding to two significant figures times the cosine of 1046 pi t. What this tells me is the induced current in the pickup coil changes with time. This gives me a function. So depending upon what moment in time I care about, that will determine what the induced current is at that moment. Now, as far as this problem is concerned, it's asking us for the magnitude of the maximum current induced. If we imagine graphing this cosine function for the current, we know it starts at a peak and oscillates between that peak value on the top and on the bottom. We call that the amplitude, if you recall from earlier. The amplitude of the function represents the maximum value of whatever the function's describing. So the maximum induced current is 0.072 amps, or 72 milliamps if you want to use the prefix. That works well also. So we have the maximum value of the induced current here. And we get the induced current because of the changing magnetic flux.